Okay. Hello, Jackson, for the introduction. So I'm Ronghui Gu. I'm now an assistant professor of computer science department at Columbia University. And I'm also a co-founder of the Certik project. You can also call it a Certik. And this is a project that aims at building fully trustworthy smart contracts and blockchain ecosystems. Okay. So we all know that blockchain is hot, and you can also view it as a keyword of the year 2017, and that is also why we're here. And during the last year, the market cap And during the last year, the market cap has been increased by 20 times. From $14 billion to $300 billion. And the number of Ethereum smart contracts have been increased to 1 million. And it's really a large number. And people are wondering why the Bitcoin and other virtual currencies has the value and why they are so expensive. And many people may answer like, well, it's all based upon trust. And someone even call it a belief. And people are trust in these protocols like the Ethereum protocol, the Bitcoin protocol, and let's say the OSS, the Algorand, these kind of like protocols. We think, well, these protocols are designed by genius, so we trust in them. However, the implementations of those protocols are not fully trustworthy, and they are vulnerable. Let's say because let's say these implementations may have bugs. They are written by average software developers. We have seen this kind of attacks almost every week, like the DAO attack, the bugs in the beauty chain, the bugs in the EduCoin, and even the bugs in the EOS, right, the system before the launch of its mainnet. And although let's say these protocols are designed by genius, but the implementation may still have bug. And according to one study done by Google, that's even let's say for the top software engineers in this world, they might make one mistake for every 1,000 lines of code. So look at the number of smart contracts out there, and you can imagine how many bugs are there, and they are managing more than $300 billion at this moment. And another thing is that, well, the smart contracts are open sourced in the sense that the hackers will look at your source code and then to attack your system. So it's quite different with the traditional system that's the attackers can only treat it as a black box. Now they can look at all the source code. So it means that if there are some bugs out there, eventually they will be figured out by attackers and then utilized by attackers. And also there's a huge attack benefits. We can see that, well, for this, the DAO, the beauty chain, the BEC, one line of a bug may lead to more than millions dollars of financial loss. So nowadays, almost all the hackers and hackers in the world, they are looking at this code and trying to get some financial benefits from the attacks. So are there any ways we can utilize to improve the reliability and the security of smart contracts and blockchain ecosystems? So I use this figure to describe some of the existing techniques. Right? The x-axis is the reliability, means how much it can help to improve the security. And the y-axis is the feasibility, means how easily it can be deployed on the blockchain. And on the left bottom corner is a human review. And someone think, well, it cannot be called as a technique, but actually it is now the mostly widely used techniques in the community to protect the smart contracts and blockchain. And of course, it cannot solve the issue, and it's also relies on huge human efforts and can't be done in a scalable way. And then we have testing on the left top corner, and it can be easily deployed, but it can only guarantee under some cases there are no bugs, you cannot attack it, but it cannot give you a very high guarantee. And then we have runtime monitor, which is also very useful in the real world, like it's being widely used in many of the digital asset exchanges, but it can't be easily deployed on the blockchain. For example, you can't run the runtime monitor on top of Ethereum because it will burn gas. It is so expensive, and it will also occupy the very limited TPS. And then we have partial verification, which is pretty powerful. Basically, we're trying to prove a list of properties of the smart contracts and blockchains. Like, well, there are no integer overflows, there are no buffer overflows, and so on. And those are I have to say that it's very helpful, but it's still far from enough. In the sense that, well, given let's say a depth, or let's say given a decentralized exchange, the properties you should prove might be different, right? And you can't say that, well, given any depth, given any piece of code, I prove the same list of properties that they satisfy. So we want to prove, like, well, it's not only free of integer overflow, but it is a correctly implemented, let's say, a decentralized exchange. And this property is what we call functional correctness. And it will be provided by our Certik project. And the technique we use is so-called fully formal verification. It's basically, it will use a mathematical way to prove that, well, the implementation indeed satisfies the specification. The specification is the design of your system. And also, then we prove that, well, your specification is correct, is free of bugs, and cannot be utilized by the attackers, and so on. And the techniques we introduce is called a deep spec. It's a layer-based decomposition way to scale the verification. And it can be done mostly automatically, and can generate machine-checkable proofs that everyone can check it on your own laptop, and can be embedded into the ledgers. So here, in 2015, so this deep spec concept was first introduced by me and Professor Zhong Shao, who is the chair of the computer science department at Yale University. And we try to use it to scale the verification. And then in 2016, this concept was widely studied by a broader community, including researchers from Yale, Princeton, MIT, UPenn. And the 2 workshops and 1 summer school have been held until now. And the next workshop will be held later this month, together with the PLDI conference. And in 2016, we developed Certik to realize this deep spec concept and build Certik, the world's first fully verified concurrent OS kernel. And in 2017, we extend our Certik technique to support the formal verification of smart contracts. And until now, 5 top-tier conference papers have been published talking about these techniques, and was also selected as a research highlight in the communication of ACM, and was widely considered as a real breakthrough. And our Certik, this fully verified concurrent OS kernel, and it can also be used as a hypervisor, was deployed on this Landshark machine, which is military robotics. And DARPA also hired a red team formed by Google engineers trying to attack the system. And after a few months attacks, in their evaluation report, they used 1 word to describe our system. They call it unbreakable. We try to utilize this technique to protect the smart contracts and blockchain. And basically, first given a smart contract or a blockchain system, we will first add labels to this smart contract. These labels work as the specifications to the contract, to the system. You can view them as a blueprint of the system. And for simple contracts like the token distribution contracts, these labels can be added automatically. And for others, we might need some formal verification expert to write those labels. And then we will decompose this labeled smart contracts into many smaller and easier to solve proof obligations using our deep spec techniques. And you can see that, well, these different proof obligations are interacted with each other, but we can focus on one proof goal at a time without worrying about the other pieces of code and the dependency relationships between all these modules. And we can focus on one module at each time. And then later, we can compose all the proofs together and deliver an end-to-end guarantee of the entire system. And then we will send each of this proof goal into our Certik network, and we will rely on the miners to help us do the proofs and also validate the proofs done by others, because those proofs are machine checkable. But all this kind of thing, this decentralized proof engine is opaque to the clients. They don't need to see how these proofs are done, how these proofs are validated. So they just need to send the proof obligation, and the thing returned is the labeled contract with the certificates, showing that, well, the contract indeed behaved as designed. The interface, and this is a PDF version, and actually you can find the video versions online. And you can see that you can simply upload the smart contracts. You click one button, and then if there's bugs, it will give you the bug report, including a counterexample of how to trigger that bugs. And this is a beauty chain bug. And if you use our tool, you can identify that bug within 1 second. And this is the bugs in the EduCoin. And also, you can we simply copy the smart contracts in their GitHub and upload using our tool to detect, and it can simply get that bug, and can also give you this counterexample. You can see that here there's a very large number which will trigger the integer overflow and cause the bug. Hello. Yeah, this is the certificate, the verification report after running the verification over the smart contract. It will give you the detailed information of your contract, your system, and will also include the labels, which are the specifications to the smart contract. And also, if there are bugs, it will give you counterexamples. And now you can use this verification report. If it said that, well, there are no bugs, it's in a very healthy stage, you can use this bug to apply for the token listing for most of the large digital asset exchanges, including Huobi, OKEX, KuCoin, Gates, Binance in the future, something like that. It's been widely accepted by these exchanges. Yeah, but however, this can't solve the issue from the root, right? We can prove many smart contracts. We can collaborate with many public chains to prove their virtual machines implementation and their code, but it can't solve the issue from the root. And then we take one step from how we think of this issue from the very beginning. When we started the Certik project, we also think in this way. We can't simply build a verified OS kernel and let you to use, because you will not use it. You will still use Linux, you will still use Windows and other operating system you prefer, and because there are many apps and so on. So we do, our Certik actually is a hypervisor. It's a very thin layer running below the OS operating systems. Meaning that you can run Linux, you can run Windows, you can run Mac OS on top of it, but this very thin layer will provide lots of reliability and security guarantees for you. So although it's a very thin layer, it can give you lots of protection. And we want to do it similarly in the blockchain world, that we want to add a so-called hypervisor chain, which is a chain of chain. And it will run under other chains. You can still run your dApps on top of Ethereum and so on, and let's say Nebulous, Neo, Qton, and so on. But hopefully in the future, our chain will become an infrastructure that's below this chains. You don't need to transfer your stuff from one chain to another chain. You can still choose the one you prefer, but we will be there and provide this formal verification techniques to improve the reliability and security of all these chains. And yeah, and that's it. And also we are hiring. We are hiring in both university, for both Yale University and Columbia University. You can join our research group. You can also join our Certik company to work with us to achieve this goal. Thank you.